Hello. I think everything is ready. Do you hear me? Do you see the desktop? Does everything seem fine?
Yes.
Okay, good, thanks. Okay, and I hear you because I have my speakers on. Okay, all right. So we're going to finish talking about virtual paging, page virtual memory today. Um, Remember that there'll be a test about page virtual memory. So these are the chapters in the book about page virtual memory. It's a bunch of short little chapters here. So these are the chapters about page virtual memory, and these are questions about page virtual memory. So we'll look at a couple of these questions later in class. So there's a couple in here that I want to show you specifically that that are worth doing in class. There's one or two that would be a good idea to do because what's the new idea in this last section here we're going to talk about today. So there's this one last section we want to talk about today, and then there's a couple problems in here that are good problems that explain some of what's in this section here. Okay, so a good way to explain this section is to do the problems that are in the review in the section. Okay, now, and I also made some more information, put some more information in some programs about virtual memory in this zip file. And some of these programs can help you a little bit with the current homework assignment. Like they show you examples of using virtual alloc. Okay, so I put some code in here that might be useful. They're nice examples for demonstrating ideas, but then they also may be good examples for you to look at for ideas of how to write the code that work with virtual memory. Okay, so there's a few C programs in here. Okay, there's 1, 2, 3, 4, 5. Well, this is the virtual memory mapper that we've been using the homework assignment. So there's this, and this one in particular, I think. Well, these here are good examples of programs that might be useful for you to look at. Okay, so what we want to do is start with this picture here and expand on it a little bit. So I'm going to download that picture so I can edit it. Okay, and I'm going to open it in the editor. Okay, so this is where we were at. We were talking about demand paging. Okay, and remember, this represents two processes running in memory. And what we've added from a couple days before was this column here about present, and we've added memory to the picture. Remember, this column present means that tells you whether a page is being mapped to the hard drive or to physical memory. Okay, a page could be mapped either over here to the hard drive or mapped to physical memory. Okay, now originally most pages start out on the hard drive. Your code is stored on the hard drive as EXE files. Okay, so your programs are stored in the hard drive as EXE files, so they start on the hard drive. Then, so when you want to run a program, you pretend the program is in virtual memory. Okay, and literally, this is what they did. You pretend the program is in virtual memory. You put the code there, say in virtual memory, but then you mark the code as not present but valid, and you point to where the code came from in the disk drive. Remember, a sector of the disk drive is the same size as a page in virtual memory. So initially, when this program is loaded, the program actually only it fictitiously seems to be in memory because it's marked as valid but not present, and then the number here would be where it is in the hard drive. But then as soon as the program counter accesses that page, as soon as the program counter touches that page, for the program counter to touch that page, it has to be in physical memory. So then you get what we call a page fault. The hardware, the memory management unit notices that this page would be not present. So the memory management unit looks up here where it is in the hard drive, picks a place in memory to put it in the physical memory. So it gets put over here. In this case, it got put in 5. Now it appears here after the CPU tried to access the virtual memory. It gets copied into physical memory, then it gets marked as present, and then the CPU can go on and start accessing this memory here. Okay. And then later on, this program might access some data. Okay. And the same thing happens here. The data might be some data that the program has on the hard drive. Okay. So it might be some data that it has in the hard drive. And the program says, put the data in my virtual memory space. So initially, when the program says, put the data in my virtual memory space, all the memory management unit says, okay, page 2 is present but not it's valid but not present. It'll become valid but not present. Okay. And then it'll be mapped to this place on the hard drive. Okay. But then as soon as the program touches the data, to touch the data, it has to, the CPU wants to load some data into its register. The data has to be in memory for the CPU to touch it. The CPU cannot talk to the hard drive. Yeah, when a page of memory is present, is valid but not present, and it's on the hard drive, the CPU can't reach into the hard drive. Okay, so when the CPU wants to access the things that are not present, they have to be brought into physical memory. Okay, so if this block here of data, when it's initially set up, it's just set up, well, it's set up to be on the hard drive. The program might tell the operating system, I want to use this data. And the operating system is pessimistic. It assumes that, well, maybe you really won't use this data. So I'll just leave it on the hard drive. I won't bother allocating it to physical memory because memory is valuable. So I won't allocate it to physical memory until you prove to me that you really need to access that data. When the CPU tries to read that data, that's when the operating system says, you really mean you're going to use this data. So then the operating system changes it from being not present to being present. The memory management unit finds an empty page over here, puts the data in the empty page. So it ended up putting it over here in 7. So then it updates the page table to say that it's present in 7. And then the CPU can go finish accessing the data. Okay. Now, so at this point, this is the stuff that's been paged. We say these are the pages that have been paged into physical memory from the hard drive. Okay. Now, for example, at this point, there's only one page left of physical memory that's empty. Okay. So if you notice over here, there's still one page here that's not present. There's one page here that's not present. So this process is allocated one page, but it's not present. So his third code page is actually over here on the hard drive, and it's valid but not present. So this program has told the operating system, I want to use that page, but it hasn't touched it yet. So over here, this one's got page 4. It's got another data page. This data page is over here on the hard drive. This program has told the operating system, I want to use that data in memory, but it hasn't touched it yet. So right now the data is, well, page 4 is not present. It's on the hard drive over here in sector 3. In sector 3. Okay. What happens if let's suppose that one of these pages in the thing it doesn't have in, and then let's see what happens when the other one pages something in. Okay, so let's suppose that this one wants the page actually accesses data 1. Okay, so when it wants to access data 1, the operating system has to say, well, I have to put this thing in memory somewhere. Well, the only place left in memory it's empty will be here. So data 1 will be brought over here. Okay. So the operating system will say, okay, here's a free piece of memory. Let's put data 1 in the free piece of memory. Okay. So data 1 is now page 4. His virtual page 4 is now present. And it's present. Okay, it's present in page. I have to update the page. This is what the operating system do. It would update the page. It would copy, the operating system would copy this block into that physical page. So the operating system would do that. It would copy this block into that physical page. Then the operating system would update the page table to say that this page now is in it went from being in sector 3 to being in page 8, oops, 8, okay? So now it's in page 8, okay, right? And now this program the CPU can continue to access that page. Okay, that was a page fault. The CPU tried to access this page. The page was not valid. So the operating system had to go grab the page from the hard drive, copy it into memory for the program. The operating system copied it into memory. After it's been copied into memory, the operating system updated the page table. And after the page table is entered, the CPU can go ahead and finish accessing that page. Okay. Now suppose you switch over here to him. And now this is where the new chapter is about. This is where the what we're about to talk about is this new chapter, policies. Hey, what do we mean by that? Watch what happens here. This program wants to access page 3, its third code page. So it's supposed to call a function in this page. This page is on the hard drive. You can't use it on the hard drive. Okay, so it needs to be brought into physical memory. The physical memory is full. So now you have to kick somebody out of physical memory. Somebody has to be kicked out of physical memory to make room for this thing that needs to be brought into physical memory. So you need a policy about who do you kick out. When it's time to kick somebody out, who do you kick out? And there's a bunch of different policies that you can be used here. Okay, so for example, you could randomly pick somebody to kick out. That's actually not considered a particularly good policy. Okay, so you could randomly pick somebody to kick out. The most common thing to kick out is find the page that's been in memory the longest and kick it out. Okay, on the assumption that if you've been in memory a long time, it's probably not. That's actually not a good policy, but it's a policy. You look for the page that's been in memory the longest. Okay. The policy that's actually in use in most operating systems is something called least recently used. You look for the page that's been the longest since it was last touched. The least recently used page. Which one of these pages was which was accessed the farthest back in the past? Now, right now, we don't have any data in this picture to say which one that might be. Operating systems keep track of this kind of thing. Okay, so what the operating system does is it keeps track. It does this with these extra bits in the page table entries. It keeps track of when was the last time each one of these was accessed. And it looks for the one that's been accessed the longest in the past, the least recently used one. Let's suppose, I'll just pick one at random. Let's suppose that this data page hasn't been accessed in quite a long time. Okay, so now if this data page is the page that's going to get kicked out, this data page gets copied back to where he came from over here. Now, when he gets copied back over to here, the operating system has to say, well, he belongs to this guy over here. So we have to make sure we keep track of that. So the data page over here is now going to get marked as not present. Okay, and I'm going to put that in red because that's happening actually while this red process is running. It's happening to him, but it's happening while the red process is running. The page, this is happening, the red process needs to bring in something. The operating system picks one of the pages from the blue process and kicks it out. When it kicks it out, it sends it back to the hard drive. It stores it back on the hard drive. So now in the hard drive, it's in page 10. So now I have to update the page table again. It's going to be over here it's put back on the hard drive in page 10, in sector 10. Okay, so it's put back here in the hard drive in sector 10. Okay, right? So now that's freed up this one. This one's free now. It got put back to the hard drive. Okay. Now the operating system can say, okay, now this one's free. Okay. This one wants to bring in code 3, this page here. So now this page here can be now marked as present. This one's going to get now marked as present. And it got pulled into, okay, it's going to be pulled into here. So code 3 goes into here, and it's being pulled into page 7. So then this one gets updated to say it was at sector 8 on the hard drive. It got copied from sector 8 of the hard drive into page 7 of memory. And then you update this one to say, okay, now it's at page 7. Okay. So that's referred to as page replacement. I replaced this page in memory. I kicked out one of his pages. I kicked out one of process one's pages and replaced it with one of process two's pages. Okay, so that's because memory was full. I needed to bring in something to physical memory, so I had to kick somebody out to bring somebody in. So that's a page replacement. And I need a page replacement policy. Okay, over here, that's called page replacement policies. What we just showed you, what I just showed you here, what we went through is the page replacement mechanism. The page replacement mechanism is take the page that's being replaced, copy it back out to the hard drive, update that process's page table, go to the page you want to bring in, copy it into physical memory, update the page table of the process that's being given a new page. That's the mechanism for page replacement. The policy for page replacement. Now, the policy, that was actually the chapter before. Okay. This was about the mechanism for page replacements. See, beyond physical memory, if you're going to use the hard drive as a substitute for physical memory, you need to know how to do it. So now he doesn't draw that many pictures in here, but he talks about the page fault and what if memory's full? See, that's what we just did. What if memory's full? See, then you need a page replacement policy, which is actually the actual policies in the next chapter, but he talks about what you do when a page is full. Okay. So here he talks about the page fault control flow. Those are the steps we just went through. That's these steps where when it's time to replace somebody, you go through this process of pick the page in memory, pick the physical page in memory you're going to use, copy what's in that physical page that's going to be what's being kicked out the hard drive, update a page table, then go back to the hard drive, copy into physical memory what's being put into physical memory, and update another page table. So there's a copy from physical memory to the hard drive, an update of a page table, then a copy from the hard drive to physical memory, and an update of another page table. That's the mechanism for a page replacement. Okay. Then the next chapter is, okay, how do you decide these things? How do you decide who gets kicked out? Okay. And the book talks about 3 policies: the optimal replacement policy, a first in, first out replacement policy. That's the one I said that you just look for who's been in memory the longest. Okay, first in, first out is whoever got put in, whoever's been sitting in memory the longest, that's who you kick out of memory. That's actually a bad policy. Okay, and then there's the then there's the one I said you randomly pick somebody to kick out. That's not a good policy. Then here's the really important one: least recently used. That's the one that's, I mean, this is least recently used is one of the cornerstone ideas in computer science. It's used in all kinds of places. You probably first see it in an operating systems class under page replacement policies, but it's also used anywhere where there are caches. It's actually a cache policy, and caches appear all over the place in computer science, in hash tables, in browsers, just in all kinds of places. So least recently used is a policy that gets used anywhere where there are caches. And essentially, this is acting as a cache. This physical memory now is acting as a cache of stuff that's over here in the hard drive. Okay, so we're actually kind of in a way mimicking a cache. Okay, so the policies are the optimal one, which is the optimal one is a fictitious policy. You can't implement it, but it's the gold standard that all other policies are compared with. And we'll show you in a minute. That's where we'll go back to the problems that are on the review sheet. We'll look at these things using the problems on the review sheet. The optimal policy is a policy that can't be implemented, but it is essentially it's the perfect policy. It's the policy that always picks the right page to read. It kicks out the right page. What essentially would be the right thing to kick out. Okay, so that policy can't be implemented. First in, first out just kicks out whoever's been in memory the longest. Bad policy. Okay. Random kicks out somebody you pick at random. Really ridiculous policy. Most books don't even mention that as a policy because it's kind of ridiculous. And then least recently used, which is the workhorse policy. That's the policy that's really used. Okay. All right. Now, let's go back to the home. Okay. There's these problems on review problems. Oops. Here's pet problems. See this problem here? This is a page replacement problem. Okay. And we're going to work through it here in a second. And we're going to work through it using, you work through the problem two ways. One way using least recently used and one way using the optimal page replacement policy. So we'll see in a minute how you do one of these homework assignments. Now, these homework assignments are kind of ubiquitous. If you open up that folder I put on the hard drive about virtual memory, and you look in this subfolder, page replacement algorithms, I downloaded from the internet. I found people who've done these problems on the internet, just like we're doing here. And here's some examples of these little page replacement problems. These are examples of these homework assignments that, this is a worked out one. This is not the one that's in this page, but this is an example of a worked out page replacement homework problem. Okay, and then I did some more examples here. Here's some more examples of one of these homework problems. So this is a worked out one, okay? Or this is several worked out ones. And these are pictures from the internet that I found somebody on a homework page had put up examples of them. So let's see how this works. Okay, I'll leave one of these up. And we'll work, and I need to download this because I need to write into this. So let me download this, save it as a text file. The first thing is to get used to the problems are set up in sort of a slightly abstract way. Okay. Each column is a representation of physical memory. So a column in this assignment, a column in this picture here. See, a column represents each row in the column represents page of virtual memory, of physical memory. So when you look at a picture like this, they're saying there's 3 pages of physical memory, which is not very many. Yeah, here, 3 pages of physical memory. Okay, that's ridiculous. Modern computers have billions of pages of physical memory. But here we're saying, suppose you only have 3 pages of physical memory. Okay, so in this picture, 3 pages of physical memory. When people do these homework assignments, they usually do 3 or 4 pages of physical memory. Okay, the top row here is called the access sequence. What that's saying is the CPU wants to access. Now, these numbers are virtual page numbers. The numbers there are virtual page numbers. Okay. The column represents physical pages. The numbers in this row represent virtual pages. Okay. The CPU wants to touch. So now what happened is the CPU is going to touch a page over here, and that page needs to be brought into physical memory over here. So in this case, there are a bunch of different, in this case, there's up to 7 virtual pages. So there's 7 pages over here and only 3 pages over here. Okay. So you imagine a picture kind of like this, where there are, in this picture, it would kind of been nice if they wrote a column of 7 pages over here. So you can imagine there's 7 pages, but there's only 3 page frames. So 7 pages, but 3 page frames. Okay, so that means that only 3 of these pages can be in memory at any given time. There's 7 of them over here, but there's only 3 places for them over here. So that means there's more over here than can fit in over here. So now what this picture is saying is access page 7. Now what that means, you read that as, okay, page 7 is brought into physical page 0. Then you access page 0, and page 0 is brought into frame 1. And then you access page 1, and it's brought into frame 2. Now page 7 is sitting here in frame 0. Page 0 is sitting here in frame 1, and page 1 is sitting here in frame 2. And these X's mean that those were page faults because you had to copy this guy into here, copy this guy into here, copy this guy into here. Now you access page 2. Page 2 is not in memory, so somebody has to be kicked out. So this one is the first in, first out page replacement policy. Of 7, 0, and 1, 7 was in there the longest. So kick him out and replace him with 2. So now that was a page fault. 7 was brought in on top of 2, and 0 and 1 are still in memory. Now the program touches page 0. Page 0 is in memory, so there's no page fault. Now the program touches page 3. Page 3, now remember, this is virtual. This is page 3 on the left-hand side. That's an actual page, the virtual pages. The columns here, the entries here are the physical pages. Okay, so over here now, page 3 needs to be brought in because he's not in physical memory. So virtual page 3, well, who's been in memory the longest at this point? Out of 2, 0, and 1, 2 just got brought in here. 1 got brought in just before 2. 0's been in there the longest. So when 3 wants to come in, 0 was in there already just recently. 2 got brought in recently. 1 was the one that's been there the longest. So now 3 is going to get brought in. Oh, I'm sorry, not, I'm sorry. This is first in, first out, not last in, first out. I was reading it. I was reading this one wrong. This one, no, it kicked out 0. It kicked out the most recent one that was brought in. Okay. No, that doesn't make sense. I wonder if there was a mistake in this page. Let's see. First in, first out would mean the first one that was brought, the one that's been in there the longest, should be the one that gets kicked out. Now, in this page, in this example, 3 needs to be brought in because it's not in. Okay. Who's in memory? 2's in memory, but 2 just got brought in. 0's in memory. Oh no, I'm sorry. This was an access to 0. 0 was brought in over here. That's why I was, yeah. This was when 0 was last touched, but this is when 0 was brought in. See, these are a little bit tricky. This was when 0 was touched. This was when 0 was brought in. So when 3 wants to get brought in, 2 was brought in right here. 1 was brought in here, and 0, page 0 was touched here, but brought in way back here. So page 0 is the one that's been in, was the first one in. So page 0 is the one that gets kicked out. Okay, so 3 gets brought in on top of 0. So now 2, 3, and 1 are in memory. Okay, now you access 0 again. Okay, but 0 is just kicked out, so it gets brought back in on 0 gets brought back in on 1 because 1 is now the one that was brought in longest to go. Okay, these things are a little bit tricky to do, but they're real simple. It's a simple idea, but okay, what you're doing is you're keeping track of how many page faults there are. Okay. Now in this homework assignment that I'm showing you here, that was from a website. Here's first in, first out. Here's least recently used. And then here's the optimal one. We'll say in a minute what the optimal one is. If you notice that this has the most page faults, this has slightly fewer page faults, this has fewer page faults. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. First in, first out will give you too many page faults. It's not a good strategy. There's no reason to kick out the page that's been in memory the longest. The page that's been in memory the longest might be the one you're using the most. You know, it might have been in the first one in because it's the one that's used the most. So the idea that you kick out the page that's been in memory the longest is actually not a good idea. It's usually in textbooks only because they need something to compare these other ones with. But there's no good reason to think that the page that's been in memory the longest ought to be who gets kicked out. okay? Because the page that's been in memory the longest might actually be, it was in there a long time because it gets used a lot. This is a good strategy. The idea is if a page hasn't been accessed in a long time, this one goes, we'll go through this one in a second. What it does is when it decides who to kick out, it doesn't say who's been in memory the longest. It says which one was accessed farthest in the past. It says, okay, maybe that page really isn't being used anymore. If it's been a long time since somebody touched that page, maybe they stopped using it. So let's kick out the page that was least recently used. That gives you fewer page faults than kicking out the first in, first out. Okay, so it's better than that. Now, what the optimal page replacement policy does, it's real tricky and it can't be implemented in hardware. Let's go through it. We'll say it in words and what it does. It's a very famous example. It's even got a name. It's called Bilati's optimal page replacement algorithm, because the guy who invented this wrote a famous paper, because then that gave people a sense of what was our goal. Our goal was to be as close to the optimal policy as possible. So then since researchers in operating systems had a way of saying, oh, how good are we? Because we can compare ourselves to what would be optimal. So here's how optimal works. Okay. Initially, you access page 7, all of memory's empty because you're just starting out. So you just load page 7. There's nobody to kick out. Right now we want to know who to kick out. Since there's nobody to kick out, you just bring page 7 in. Now you access page 0. You don't have to kick anybody out. Bring 0 in. Access page 1. There's nobody to kick out. Bring page 1 in. Okay. Now we want to bring in page 2. We have to kick somebody out. We have to kick out 0, 7, or 1. One of these 3 has to get kicked out. We're going to kick out the one that will be used in the future, farthest in the future. Okay, so when we bring in 2, out of 1, 0, and 7, we say who's going to get used the most distant in the future. Well, 0 is going to get used soon, so we don't kick out 0. Well, 3 is not even in memory. 0 is going to get used again here. 4 is going to get used here. Now, we're looking for 0, 1, and 7. Who of these is going to get used the most distant in the future? Who do we kick out to bring in 2? Well, 0 is going to be used right away. 1's going to get used over here. Oh, and look here, 7's not going to get used again till way over here. This is the first time 7 gets used again. So 7's going to get used way in the future. So let's kick out 7. So 7 gets kicked out to bring in 2. Okay, so 2 replaces 7 because 7 is not going to be needed for a long time. Now, you have to look into the future to be able to do that. But as an experiment, you can, now what people can do in the real world, they can compare themselves to the optimal policy by writing in memory a history of the page accesses, and then look at what they actually did, and then compare it to what would have happened if they used the optimal page replacement policy by keeping a history of what they did. And operating systems people do this stuff. Microsoft does this stuff. By keeping a history of what the page accesses were, they can compare the history to what would have been if they'd used the optimal policy. Okay. So 2 gets brought in on top of 7 because 7 is not going to get used way over to here. Okay. Now 0, well, 0's in memory, so that's not a page fault. Now we need to bring 3. Now 3 is not in memory, so we need to bring in somebody. Now who's in memory is 2, 0, and 1. Now we want to bring in 3. Out of 2, 0, and 1, who's going to be used the farthest in the future? 0 is a pretty active page. 0 is going to be used right away again. So we're not going to kick out 0. 2 is going to be used a little bit farther in the future. So 0 and 2 are going to be used. Like here's 0 is going to be used. Here's 2. Then you look down here. Oh, 1's not used for quite a while. So 1 is going to be the one to kick out because 1 isn't going to be used for a long time. So when 3 needs to be brought in, it's going to be brought in on top of 1. See, it's going to be brought in on top of 1 because 1 wasn't going to get used till all the way out here. 0 is going to get used next. 2 is going to get used soon after that. So 0 and 2 were in memory and they were going to get used pretty soon. 1 wasn't going to get used for a long time, so replaced 1. Okay, so that's the optimal page replacement algorithm. Okay, now let's do it in a homework assignment ourselves, where instead of looking at somebody's answer, let's do one over here. Okay, so the columns here represent the physical pages. The numbers here represent page, these numbers represent pages. These columns represent page frames. Okay, so I'm going to access 0. Now memory is empty, so I'll just put page 0 in frame 0. Okay, then I'm going to, now page frame 0 is in page, see, now I go here. Now I need to access page 1. I'll put page 1 in frame 1. Okay, now I need to access page 2. Well, 0 stays where he is, 1 stays where he is, and page frame 2 is empty, so I'll bring in 2 in 2. Okay. Now, this is starting up the program. Notice when you start up a program, it just page faults itself in. So 0, 1, 2 got page faulted, page faulted, page faulted in. And if I want, I can count. That's a page fault. That's a page fault. That's a page fault. Usually when people do these, they put a little X at the bottom of the things that are page faults. Some people put the little X at the top. You could also go over here and say, you can put the page faults here. That was a page fault. That was a page fault. That was a page fault. Keep track of the page faults. Okay. Now, access page 3. Well, page 3 is not one of the pages in memory. We have 0, 1, and 2 in memory. So who will we kick out? Now, in the problem here, it says to use says use least recently used in the first table. Let's see. Oh, I'm saying, yeah, use least recently used in both. There's 2 examples here, and it says to use least recently used in both examples. Okay, so this is instead of, sometimes I'll ask you to compare least recently used with the optimal. In this case, it's just 2 different examples, and you do both of them with least recently used. Notice that this sequence is different than this sequence. If they were the same sequence, then you probably would want to compare 2 different algorithms. If they're 2 different sequences, then you're just doing the same algorithm 2 times. So in this case, we're going to do least recently used. Okay, right? So now, out of 0, 1, and 2, that's who's in memory now. Okay, we want to bring in 3. Do we kick out 0, 1, or 2? Who was accessed in the most distant past? Well, that was 0. Yeah, so we kick out 0. So we're going to leave 1 in place, leave 2 in place, and bring in 3 on top of 0. Now, in a real example, 0 would be copied back out to the hard drive, and then 3 would be copied in its place. So this page would be copied to the hard drive. This page is getting copied into physical memory. Okay. Oh, and that was a page fault. Okay. Now we access page 0. Well, we just kicked page 0 out a little while ago. Notice that this is, notice that if the optimal strategy would not have kicked out 0 because 0 is going to get used right away next. See, the optimal policy would not have kicked out 0 because it was going to get used. 0 was the least recently used, but it was also about to be used next. Okay, so 0 got kicked out. So that means, okay, now who do we kick out now? Well, we kick out the one who was the least recently used. Well, if we go back, 2 is in memory, was just used a little while ago. 1 was used just before that. So 1 was the one that was least recently used. Okay, so we want to bring in 0. Okay, in memory is 3. 3 was just brought in, so he's pretty recent. 1 was brought in before 2. See, 2 is brought in here. 1 was brought in here. So 1 is the one to kick out. So we leave 3 in memory. We leave 2 in memory, and we kick out 1, and we replace 1 with 0. Okay, and that's a page fault. Okay, I'll put the page faults up on top. Okay, now let's go to this one. Okay, now we need to bring in page 1 because page 1's not in memory. Notice we just kicked it out. If you notice that there's something funny going on here, see how it's going 0, 1, 2, 3, 0, 1, 2, 3. This is a program that steps through memory in a cycle. It touches page 0, then page 1, then page 2, then page 3, then page 0, then page 1, then page 2, then page 3. and it's using least recently used. This is least recently used as nightmare. When you're cycling through memory, you end up kicking out exactly the page you're going to touch next. If you look at it, what we're doing right now is we're always kicking out exactly the page that we're about to touch next. Like here, we're going to access page 1. And next, we're going to access page 2. But when we access page 1, the page that was least recently used is page 2. Because in memory is 3. It just got brought in. So 3 is going to stay there. In memory is 0. 0 was brought in. Let's see. I'm sorry. Zero was just brought in. See, 0 was just accessed. So 0 was just brought in. So we're going to leave 0 there. 3 was brought in just before 0. So we're going to leave 3 there. And 2 was the one that was brought in earlier. See, we go backwards. 0 was just brought in. 3 was brought in before that. 2 was brought in. So 2 was the least recently used. But notice it's the next one to be used. So we're going to kick out exactly who we need next. And this is actually why least recently used. This is one problem that least recently used has. If you're cycling through memory, it could end up kicking out exactly who you need next. Okay, so that's a page fault. Okay, now we want to go to page 2. Okay, we want now 2 is not in memory, so 3, 0, and 1 are in memory. Okay, we've got to kick somebody out. Okay, we just brought in 0. We just brought in 1, so we're not going to kick out 1. Before 1, we brought in 0, so we're not going to kick out 0. Okay. The one that's been in memory the longest is 3. That's the least recently used. So we're going to kick out 3. But notice that 3 is exactly who we're going to use next. So we get another page fault. Notice that we're page faulting on every access here. Okay. And then the last example, the last column will be we want to access 3. Okay, 3 is not in memory, so we have to kick somebody out. We just brought in 2, so we're not going to kick out 2. Just before 2, we brought in 1, so we're not going to kick out 1. So 0 was the one that was the least recently used. So we bring 3 in on top of 0, and that's another page fault. So we page faulted on every access. Okay, let's do another example. Let's do a more complicated example. Let's do this one. This one's a more complicated example. Okay, this one I didn't set up the table. So to do this one, you have to like set up your own table. So I'll do this one. I'll do a little bit of copying and pasting here. So I'll set this one up. I need 4 page frames for this one. I don't remember. I should have set up a table for this one, but I forgot to set up a table for it. Okay, so now I made my table for it. Okay, so there's a table, and the top row is the page reference. So I'll make this table look like the other one. Okay, so now I've got 4 page frames, and I want to access. Now notice that it looks like there's 7 pages, and there's only 4 page frames. The pages are going to get accessed in this order. Okay, now the problem says use first in, first out, least recently used, and the optimal one. So you actually need 3 of these you need 3 of these tables. So if I'm going to set this up, I would do this table 3 times. Okay. Okay. So do this one using first in, first out. Then this one will be least recently used. And then do this one as the optimal. Okay. So do the same sequence 3 times and keep track of page faults. So this last column down here, you could say keep track of the faults by putting a little X in put an X where there's faults. Okay, see, so keep track of where the faults are. Okay, so here I set it up with a nice table. So now I can do the problem with a nice table. So let's start each one of them. We'll do a few of each one to see how the algorithms differ. Okay, the first in first out is going to give you the most page faults. Least recently used is going to give you something in between, and the optimal one will always be the least number of page faults. You can't do better than the optimal, and that's actually a theorem. Somebody actually proved that the optimal algorithm truly is optimal. If you're allowed to look into the future, you can do exactly the perfect thing. Kick out the page that's going to be used the most distance in the future. And somebody actually proved that that really is the best you could do. Okay. All right. So, okay. Now, initially, memory is considered as empty. So 0 will be brought into frame 0. Then it'll stay put, and 2 will be brought into page frame 1. Okay. Then it'll stay put. Okay. Now, 0 will stay put here, 2 will stay put here, and we'll bring in 1. Now, we haven't filled up physical memory yet, so nobody's going to get kicked out. Now we bring in 3, leave 2 where he is. I'm sorry. Leave 0 in place, leave 2 in place, leave 1 in place, and bring in 3. Okay, now that was page fault, page fault, page fault, page fault. That was 4 page faults right away. So memory was empty, so you fill it up. So if you're filling up physical memory, page fault, page fault, page fault, fill up physical memory. Okay, now we've got to kick somebody out. Memory's full. We want to bring in 5. Okay, who's been in memory the longest? We're using first in, first out. 0 was the first in, so we're going to kick out him and replace him with 5. And 2 stays there, 1 stays there, 3 stays there, and that was a page fault. Okay. Now 4 is not in memory, so it's got to be brought in. Somebody has to be kicked out. Who's been in memory the longest? Well, if we go back, 5 just got brought in, 3 was brought in before that, 1 was brought in before that, and 2 was brought in before that. 0 is gone. 2 is the one that's been in there the longest. So 2 is going to get kicked out. So 5 stays where it is, 1 stays where it is, 3 stays where it is, and 4 is brought in on top of 2. Okay. All right. Now we need to bring in 6. Oh, and this was a page fault. Okay. Now we need to bring in 6. Okay. 6 is not in memory, so somebody has to be kicked out. Okay. So now we have to think we need to kick out who's been in memory the longest. Okay. 4 was just brought in, 5 was just brought in. Now, you got to be careful. Remember, I'm not supposed to count when these are accesses, but we know that these were also page faults. Later on, as we go farther in, you have to be a little bit careful. You don't just look for which number was farthest in the past. You have to distinguish between accesses and when it was brought in, when it was page faulted in. We need to know who was brought in most distant in the past. 5 was brought in that page fault. 4 was brought in on that page fault. 1 was brought in on that page fault, and 3 was brought in on that page fault. So 1 is the one that was page faulted in first. So 3 will stay put, 4 will stay put, and 5 will stay put, and 6 will come in on top of 1. Okay, and that's another page fault. Okay, now 3 is there. So the way we do that is we say everybody stays put. We don't need to kick anybody out. So 5 stays where he is, 4 stays where he is, 6 stays where he is, 3 stays where he is, and that's not a page fault. Okay. Now 7 needs to be brought. Now 7 is not in memory. So who is in memory the longest? Okay. Now don't look at this because this was not when 3 was brought in. 3 was brought in back here. Okay. So 3 was brought in back here. 6 was brought in here. 4 was brought in here. 5 was brought in here. It's actually 3 that was brought in. 3 has been in the longest, even though 3 was accessed right here. See, if we were using least recently used, we wouldn't kick out 3 because 3 was used real recently. but 3's been in memory longer. So if we're using first in, first out, we kick out 3 to bring in 7. So this is where first in, first out is going to differ from least recently used. 3 was just touched, but he's been in the longest, so we kick him out. Okay, that's why this is a bad policy. If you just touch 3, you're probably using him. See, if you just, that's why the intuition of least recently used is the pages you touched in the recent past are the pages your program's using. It's the pages you haven't touched in a long time that should be kicked out. Okay, not the pages that have been in memory a long time. It's the pages that haven't been touched in a long time. So first in, first out's a bad policy. No operating system would really. It's only advantage. Oh, why is it even mentioned? There is a good reason to use first in, first out. It's easier to implement. If you're designing cheap hardware, like you're trying to design a CPU that can be sold for 5 cents, you might want the cheapest possible memory management unit to use fewest transistors. First in, first out's easier to implement than least recently used. So it might be the case that a really cheap CPU that's trying to keep costs down as much as possible and use as few transistors as possible might implement a simpler algorithm. Okay, so you can imagine that there might be a reason to be using first in, first out. But the only reason to possibly use it is it's a simpler algorithm, so you can implement it with less hardware. Okay, all right, now, so here we need to, 7's got to be brought in. We're going to kick out 3 because 3 was brought in, of the pages in memory, 3 was brought in the longest to go. So 6 stays put, 4 stays put, 5 stays put, and 7 comes in on top of 3, and this one is a page fault. Okay, all right, now we're going to access 4. 4 is in memory. So 5 stays put, 4 stays put, 6 stays put, 7 stays put, and that's not a page fault. Okay, 7's in memory. So 5 stays put, 4 stays put, 6 stays put, 7 stays put. That's not a page fault. Okay, now 3 needs to be accessed. 3's not in memory. So now we have to ask who's been in memory the longest. And we don't look at access, we look at when it was loaded. When was 5 loaded into memory? 5 was loaded right there. Okay, 4 was loaded right there. Okay, 5 was loaded there, 4 was loaded there, 6 was loaded there, 7 was loaded there. So it's actually 5 that was loaded the longest ago. 5's been in memory the longest. So we're going to kick out 5 and replace it with 3 and leave 4, leave 6, leave 7, and that was a page fault. Now 3 gets touched again, so everything stays put. And that's not a page fault. Okay. Now 5 is going to get touched. Okay. Now notice we kicked out 5 just a second ago. See, the optimal algorithm would have noticed that 5 is going to get used real soon, and the optimal algorithm wouldn't have kicked out 5. Okay. But in this case, here's who's in memory, and we kick out who's been in memory the longest. 3 was brought in this page fault. So you don't, yeah, this page fault brought in 3, so 3 was in there real recently. 4 was brought in by that page fault. Notice that 4 is not a page fault. That's an access. The thing that brought in 4 was the one here with the page fault. So 4 was brought in back then. So 3 was brought in here, 4 was brought back in there, 6 was brought in right after 4, and 7 was brought in right after 6. So 4 is the one that's been in there the longest. So 3 stays, 6 stays, 7 stays, 4 is the one that's going to get booted out. It's the one that's been in there the longest. So 5 goes in place of 4, and that one is a page fault. Okay, then no page fault here because you access 5 twice in a row. Okay, all right. Now, okay, let's stop that one. Let's do a few steps of not if you do least recently used, not much is going to change here. We kind of notice which ones will change. Let's go ahead and let's do the optimal one. Let's do this using the optimal one. Let's do an example doing optimal. Okay. At the beginning, nothing changes. You'll bring in page 0 on top of 0, and it'll stay there for a while until things fill up. 1 is going to be brought in here and stay there until things are full. 2 is going to be brought in. Oh, I'm sorry. It goes 0, 2, 1. Okay. So 2 is going to be brought in here and stays there. Okay. Then 1 is going to be brought in and stay there. And then 3 is brought in. Okay. So that starts things off. 0, 2, 1, 3. Nobody gets booted out yet. Okay. Now 5's got to come in. Who do we boot out? Okay. Remember, we boot up here, we booted out 0 because it came in first. That was first in, first out. Least recently used would also boot out 0 because 0 hasn't been touched since back then. So both first in, first out and least recently used would boot out 0. The optimal one says, okay, 0, 2, 1, and 3 are in memory. Who is going to be not used the most distant in the future? Okay. So 0, when's he going to get used in the future? And if you notice, 0's never used in the future. Okay. So he's used essentially infinitely far. So probably 0 is going to get booted out because 0 is never used in the future. What about 2? 2 is going to be used here, pretty far in the future. 1 is going to get used here, and 3 is going to get used here. So 3 will be used soonest, 1 will be used a little after that, 2 will be used after that. 0 is never going to get used again, so we boot out 0 because that's the optimal thing to boot out. It's never going to get used again. So 5 will replace 0, 2 stays put, 1 stays put, 3 stays put, and so far everything has been a page fault. That's been a page fault, page fault, page fault. Page fault, page fault. Okay. Okay, now we have 4. 4 is not in memory, so we have to kick somebody out. So 5, 2, 1, and 3 in memory. Who's going to be used the most distant in the future? 5 is going to get used there. 2 is going to get used there. Oh, so 2 is farther out there than 5. So 2 is the candidate so far to boot out. 1 is going to get used there. So 2 is the candidate for being booted out. 3 is going to get used there. So, and there. 3 is going to get used there. So the one that's going to be of 5, 2, 1, and 3, the one that's going to use most distant in the future is 2. So kick him out. Okay. So keep 5, keep 1, keep 3. This is a page fault, and we're bringing 4 in on top of 2. Okay. All right. Now we need 6 brought in. 6 is not in memory, so we have to boot somebody out. So we do the same thing again. 5 is going to get used here. 4 is going to get used sooner. So 5 is the candidate. 1 is going to get used here, which is after 5. So 1 is the candidate. And 3 is going to get used here. So 1 is going to be used the most distant in the future. So 1 is the candidate to get kicked out. So 5 stays put, 4 stays put, 3 stays put, and 6 gets brought in on top of 1, and that's another page fault. Notice that so far everything's page faulting, even in the optimal strategy. Okay, now we need to access 3. 3 is in memory. Okay, so 5 stays put, 4 stays put, 6 stays put, 3 stays put. Now we need to access 7, and that wasn't a page fault. Now we need to access 7. 7 is not in memory. Somebody's got to get kicked out. 5 is going to get used there. 4 is going to get used sooner. So 5 is a better candidate. 6 is going to get used never. 6 is never going to get used. So 6 is going to get booted out because 6 is never used again. So we should kick out 6. So keep 5, keep 4, keep 3, and boot out 6 and replace them with 7. Okay, and that was a page fault. Okay, now 4 is in memory, so 5 stays put, 4 stays put, 7 stays put, 3 stays put. 7 is in memory, so 5 stays put, 4 stays put, 7 stays put, 3 stays put. 3's in memory. Notice that by using, we've kind of, at this point, we're kind of coasting because we didn't boot out anybody that we shouldn't. So now what we want in memory is in memory. Okay, so notice that we've kind of got memory to the where it's holding what needs to be there. So the optimal strategy, once it's got, it kind of settles on pages that could be really used. Okay, notice now 5's in memory, so we keep 5, keep 4, keep 7, keep 3, no page fault. 5's memory again, so 5 stays put, 4 stays put, 7 stays put, 3 stays put. 3's still in 3's in memory, so 5 stays put, 4 stays put, 7 stays put, 3 stays. Now compared to first in, first out, notice how we have the same number of page faults to begin with as first in, first out. But now we've kind of got things in a better place, and now we're doing much better than first in, first out. Okay. And finally, somebody's got to be brought back in. See, 1 hadn't been used in a long time. Now it needs to be brought back in. So now we have to kick somebody out. Okay, 5, never going to get used again. 4 is going to get used here. 7's going to get used here. 3 is going to get used here. 5's never going to get used again. So kick out 5 and bring in 1. Keep 4. Keep 7. Keep 3. And that was a page fault. Okay, now keep 1. Keep 4. Keep 7. Keep 3. Keep 1. Keep 4. Keep 7. And keep 3. 7's in memory, so we keep 1 and 4 and 7 and 3 in memory. Oh, now we need somebody brought in. 2 needs to be brought in. Oh, so none of these were page faults. 2 needs to be brought in. Okay, so we can kick somebody out. 1 will be used here. 4 will be used here. 7's never going to get used again, but 3 is going to be used here. So we should kick out the 7 because it's not going to get used. So we'll bring in 2 on top of the 7. Keep 3, keep 4, and keep 1. And that was a page fault. Okay. And then 3, 4, 1, there's 3, 4, and 1. So there's no more page faults. Okay. So we only had these page faults. The rest of these, see, then you'll keep 1, 1, 1, 4, 4, 4, 2, 2, 2, and 3, 3, 3. Okay. Now, if you finish the least first in, first out, there'll be several more page faults here. You can do least recently used, and there'll be a fair amount of page faults here. This will be the minimum number of page faults. By being very strategic, by looking into the future, you can kick out pages real strategically, and you get these long runs where you have exactly what you need in memory. Okay. All right. So there are the 3 most important page replacement algorithms. They're called policies. They're really algorithms. Each one of them is an algorithm telling you what steps to take to decide who to kick out. The mechanism, okay, the mechanism is this picture we drew here. The mechanism algorithm is what steps does the hardware take? Where, remember, the mechanism was somebody in physical memory gets copied to hard drive, a page table gets updated, then something from the hard drive gets copied into the page frame, and then a page table gets updated. Okay, so you update the page table who's being booted out of memory, and then you update the page table who's getting something brought into memory. Okay, that's the mechanism. And then the algorithm is, the policy is, but who do you kick out? When memory is full like this, how do you decide who to kick out? Okay, now there's one last thing here that that you can look at in this picture here and think about this. In this picture here, we kind of assume that there's just one process running. Over here, I have 2 processes running. And this is actually kind of important. when the red process needs to bring in something, should the red process be allowed to kick out somebody from the blue process? Or should the, like, suppose you use least recently used. Should the red process only use least recently used on its own frames, or should the operating system do least recently used on all the frames? Should it kick out the red process's least recently used frame, or should kick out the anybody's least recently used frame? And different operating systems take different points of view on that. Those are called local versus global page replacement. If the red process if the operating system will only kick out a red frame to make room for a red frame, that's called a local page replacement algorithm. The red process can't cause a blue frame to be kicked out of memory. I think most operating systems use the global replacement policy. When you need to bring in a red frame, kick out someone who just hasn't been used in a long time, even if it's a blue frame. Because if the blue process hasn't used one of its frames in a really long time, it probably isn't really using it. So I think most operating systems, I think they use a global policy. But you could imagine that you'd say a red process, when it wants to bring in a page, can't kick out a blue process's page. In fact, in the real world, it's probably more complicated than that. They probably use global policies, but using priorities. So I'll bet that a red process can't kick out a page from a blue process that has a higher priority. It probably can kick out a blue frame if the blue frame has lower priority. If blue is a lower priority process than red, then the red process can probably kick out one of its frames. So in the real world, it's probably something more complicated like that. Like maybe you have a global replacement policy, but only with processes that are lower priority than the one that needs to have something brought in. Okay. So the book mentions that a little bit. The book mentions at some point that there's a distinction between global and, let me see if I can. That's mechanism, policy. Let me see. Locality is a different idea. Locality is not the idea of a local policy. So he's talking a lot about locality. No, he doesn't talk about, yeah. No, yeah, he doesn't mention that in this book. Yeah, there's probably another operating system book to point out that the policies could be either local or global. So actually, I forgot. He doesn't even mention that in here because it's not considered a real important thing. But it is an idea that you could come up. You might ask, is it fair for the red process to house one of the blue processes page to be kicked out? And the answer is pretty much yes. I'm pretty sure that in most operating systems you do allow that, but I think that in fact that they actually, but they might put restrictions on policy, on priority. Okay, now let's see what else do we want to. Now let's look at. I said that there was some code in that folder that could be useful. So let's look at in this folder that I downloaded. Okay, so this is the folder from here, this virtual memory using paging folder. So I download that zip file and I unzipped it. Okay. Now there's a bunch. People have lots of interesting like these are. I just downloaded examples of people who've written other pictures about paging, and I think some of these are very nicely done. So I mean, I just downloaded a few of them. So if you want, you can look through these. I think they're nice summaries of some of them are. There's a little bit of redundancy in these. Okay. Yeah, this is the same guy. These are just two different things by the same guy. This Matt Walsh is really well known for his writing on Linux. So he teaches a course in operating system, and he also wrote some famous books on Linux. And he does some nice things in his courses. He creates some real nice slides. And see, it's this guy here. He's actually he teaches it. I don't think he's there anymore, but he used to teach at Harvard. But he also wrote some really good open source books on Linux, and so he became famous for like writing the go-to book on how to get started with Linux. So I think the name of the book was Getting Started with Linux. Yeah, but I don't know if it's still in print, but it was a really, really, really good book. I don't even know if it's still in print, but that's one of the things he became famous for. So this is another. So there's a bunch of his pictures of examples of his explanations of these paging algorithms. Okay. Okay. Now here's an interesting program. This is a C program that does what it does is it tells the operating system to take every page of a process and kick it out of physical memory. It's called trimming the pages. It's a weird thing to want to do, but Windows lets you do this. You can tell Windows to take every page, like right now, this process has a page here, 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 here. They're in physical memory. This program calls a function set process working set size, okay, that tells Windows to set this program to have 0 pages in physical memory. So it tells the operating system to take all the pages that process has in physical memory and kick them out of physical memory into the hard drive. At that point, if the process wants any of those pages back, it has to page fault them back in. Okay, so when you run this program, it sends all the pages of a process to from physical memory to the hard drive. Then the program has to bring them back in. Okay, now let's see. You can watch that happen. Okay, so if I open up a command prompt here, I can run this program, trim pages. Now, the trim pages program wants to know what process it should do this to. So I go to Task Manager, and I pick a process. I'm going to pick one of these Chrome processes. Notice it's not page faulting right now. Okay, it's not page faulting, but it's process number 47456. Okay, so let's see what happens if I 47456. Now what I'm going to do is tell the operating system to take that process there and just kick all of its pages out of physical memory back to the hard drive. Now, if the process is active, I don't even know if it's really active now, it will need to page fault things back in. So I'm not sure. It may not be active. Okay. Oh, I think I can't. You know why I can't do that one?
You put the wrong ID.
Yeah, that's not me. Yeah, no. Oh, did I type in the wrong number?
Yeah.
Oh, I typed in the wrong number. Okay. It's what? 47456. Okay. No page faults. So it wasn't an active process. Let me pick something that's active. Let's do this on something that's running. Actually, why don't I just do it to this? I'll do it to this command prompt itself, because that prompt is something I'm using. So let me do it to that command prompt itself. Make sure that's the current one. Yeah, so this is this process right here. So let me tell this program to trim this process's pages here. So I'll trim 60052. Notice he's not page faulting right now. He's kind of stable. See how he had to page fault 287 times? Because he's running clearly, but he got kicked out of memory, so he had to be brought back into memory. So watch again. I'll trim him again. So I trim him, and 400 page faults to bring him back in again. Notice that if I keep trimming him, I get different numbers of page faults to bring him in. I'm not sure why. See, that time it took 403 page faults to bring him back in. That time it took 411 page faults to bring him back in. 403, 404. Okay, so what I'm doing is I'm actually telling the operating system, this program's got a bunch of pages in physical memory. Kick them all out. But the process is running, so it needs those back in physical memory, so it page faults them all back in. Okay. Now, what's interesting about this is sometimes programs accumulate a bunch of stuff in physical memory that they're really not using because you have so much physical memory. So occasionally you could trim a process and it'll page fault back in only a fraction of what it was using before. So you would see its memory size decrease. Who knows which one? I mean, I don't know which ones of these are active. Like, let's do this Dropbox one. It's kind of active. It's using a lot. It's using a fair amount of memory. Let's see if it's just. Let's see if there's a if this Dropbox one. Five eight nine five two. See, 1,000 page faults. I wasn't checking to see if this number went down. Oh, see, they went back up again. See, it needed more. It's starting to recover. You know, it's noticing that it was trimmed, and it just see there a whole bunch more. See, notice how it said I need to get this memory back again. So look, see, it's growing because it's page folding a bunch of stuff back in. I could go trim it again. Then it needs to do a bunch of page faults, more page faults, more page faults. It needs to be bringing itself back in again. So that Dropbox process, you know, in this case, trimming it was not a nice thing to do to it. It has to do a lot of work now to bring itself back in. And it doesn't seem to, it seems to be bringing back in just as much as it was before. Okay. I don't know. I should have paid attention to see if that number is smaller than what it was when we started. I think it is now smaller than what when we started. So I think its memory footprint now is smaller than it was a minute ago. Okay. Right. Now let me show you one last thing. Another program that's in this folder is this program called Memory Loop and Memory. Memory Loop is a lot like your homework assignment. Memory Loop is in a loop where it allocates and deallocates memory. So see, it reserves memory, commits the memory, touches the memory, frees the memory, and then it does that all over again. So it's just in a loop of reserve. And it's the same memory location over and over again. Reserves, commits, touches, frees, release. Reserve, commit, touch, free, release. So it's just in a loop of doing that. And then you could watch this thing with a memory mapping program. You could run this program, the memory loop. Okay, it's looping in memory. Yeah. And then if I want, I could launch this memory mapper. I could launch the memory mapper. Where is it? Oh, VM mapper, I'm sorry. I could launch the VM mapper, but I need to know his process ID number. So go to the task manager. This is called memory loop. There's memory loop 47112. Now, whoops. You have to find where in virtual memory he's doing his steps. I forget. You have to go but you could see it happening in here. You could see this thing constantly allocating and allocating, releasing the same memory. But I forgot what memory addresses it's working with. It's working on, oh, here, this one here. It's at 5. Well, I forget where I thought it was over. I thought it was this block here. I thought it was this block here, but it's not showing up in here. But we're out of time. But this code here, this memory loop code, I wrote it to be, give you a good sense of what you would do in the homework assignment. So here's an example of a reserve, an example of a commit, an example of a touch, an example of a free, an example of a release. Okay. Yeah, it's a simplified version, but it shows you an example of each one of those. And it should be showing up. We run out of time, but it should be showing up in the virtual memory map. I probably should rewrite this one to put I should rewrite this one to put the stuff happening like before in the middle of this big, huge region here. That makes it easy to find it. So I think I'll rewrite this one to do its work in the middle of this big chunk of free memory here, because then it becomes easier to find it as opposed to wherever I put it now. I'm not sure where I put it. I forgot now where it is. Somewhere. Did I map the right ad? Did I even map the right things? It doesn't seem like anything's happening. Okay, well, we should quit there. Okay, so if you have questions about the homework or the review, come to office hours or send me an email. Oh, that's why it wasn't updating. Something went wrong. Oh, that's why it wasn't showing anything. It wasn't updating. It was blocked. Okay, there. See, now you can see it doing stuff. See? Yeah, right there. See? Yeah, see, there's it was blocked. That's why it wasn't doing anything. See, now this is see, commit reserve. Now it freed the memory. Now it reserved it. Now it committed it. Then it touches it. Then it decommits it. Then it frees it. Then it allocates it again. Okay, see, it's just in a loop. I think I'll change it to be in the middle of this big free block instead of being on one end of it. Okay, so there's somehow I managed to block this process so it wasn't being, the GUI wasn't being updated. Okay, all right, so that's a good example because it shows you the kind of code you need to write in the, remember, it's memory loop in this folder here. Okay, so I should quit. We've gone over. So if you have questions, please send me emails. And this is the end of the semester. I'm sorry. This is the last day we meet. I forgot. So the exam will be, we won't meet next week. So, and the exam will be just like the other exam was. You'll find it on Brightspace. I'll be in a meeting. I'll be available all day. So if you have questions, you can always meet me in Zoom that day, or you can send me emails. So I'll be available that day to ask questions either over Zoom or by email. So definitely that'll be the case. And otherwise, it's a messy semester. Hopefully next year we'll be back to normal. It's looking good for next year. Hopefully next semester will be okay. And I think things went about as given how bizarre everything is, I think things went reasonably well. If you have questions though, please go ahead and write to me. So otherwise, good luck in final exams and have a nice summer. Okay, so I'll end the meeting now. Bye-bye. Yeah, somebody have a question?
What time will the exam open?
Oh, I haven't even, probably like 9 in the morning.
Okay.
Yeah, I'll just make it available in the morning and do in the evening.
Okay.
So you have the whole day to do it. Okay. So, okay. Just, I think, well, when was the last one? Well, whatever. It'll be available in the morning and you'll have till the evening to do it. Okay. Well, any other question? Any other questions? Okay. Like I said, good luck with the rest of the semester and have a nice summer. Bye-bye. And hopefully see you next year.